Today's topic is average atomic mass calculations. Our learning targets include being able to explain the difference between mass number and average atomic mass, being able to calculate the average atomic mass given an element's isotopic masses and relative abundances. And for honors chemistry classes, we will be able to calculate the relative abundance of the isotopes of a given element. Let's begin by talking about atomic mass units, or AMU, also known as unified mass units. So unified mass unit, with the U abbreviation here, that is the SI unit for atomic mass in chemistry. So commonly you will see AMU and U, those symbols used interchangeably, and they basically mean the same thing. The unified mass unit is a more contemporary version of the AMU. So just understand when you see AMU or units, they mean the same thing. So we use atomic mass units or unified mass units to express the mass of an atom. Why isn't the mass of an atom expressed in grams? Well, the main reason is because atoms have extremely small masses. So if you take an element like carbon, for example, and you find the mass of an isotope of carbon, such as carbon-12, the mass of it in grams is approximately 1.992646547 times 10 to the negative 23 grams. That's an extremely small number. It is a very cumbersome number to use in calculations and to recall. So because it's so inconvenient, we use unified mass units or atomic mass units to express the mass of an atom. So carbon then has an average atomic mass of 12.0111 atomic mass units or unified mass units. So that's the number that appears on the periodic table. The International Union of Pure and Applied Chemistry, IUPAC, defines the unified mass unit or the atomic mass unit as 1/12 the mass of a carbon-12 atom in its ground state. So 1 unit equals 1.66054 times 10 to the negative 24 grams. That's the actual mass of a unit or a unified mass unit. Since one atomic mass unit or unified mass unit equals 1/12 the mass of a carbon-12 atom, the mass of a carbon-12 atom equals exactly 12 units or 12 AMU. So carbon is just the basis, the carbon-12 isotope is just the basis of the atomic mass unit. Most elements in nature occur as a mixture of isotopes. So for most elements, one isotope is usually more abundant than the others. And you can identify this isotope by rounding the average atomic mass to the nearest whole number. So let's take a look at these three elements: titanium, vanadium, and chromium. So if you look at the periodic table, you'll notice that this value right here, this is known as the average atomic mass for that particular element. Okay, if you were to take that number and round it to the nearest whole number, you would get 47.867 would round to 48. Okay, so 48 you'll notice is right here. 48 is the most abundant isotope of titanium, titanium-48, available in nature. And that's evident and shown in this pie chart. So this dark blue region right here that I'm going to shade in with green, with my green highlighter, this dark blue region that's now shaded in, that is the section of the pie that titanium-48 occupies. You can see it takes up the majority of the pie chart. But there are also other isotopes of titanium available in nature, and they include titanium-46, titanium-47, titanium-49, and titanium-50. So these numbers, these perfectly round whole numbers, okay, they represent the mass number. So this is the mass number of an isotope, not to be confused with the average atomic mass. Let's take a look at another example. So vanadium, in the next element listed, has an average atomic mass of 50.9415. If you round that to the nearest whole number, That is 51. And you can see that right here, that it's the more abundant isotope present in this pie chart. So the majority of vanadium present in nature is vanadium 51. And you can see vanadium 50 has a very small presence in nature. Okay, we're going to look at chromium in a little bit more depth, but hopefully you can see that if you round 51.9961 to a whole number, you get 52, and 52 is the most abundant isotope, chromium 52, available in nature. Okay, so for most elements, you can usually tell by looking at the average atomic mass what the most abundant element is in for most elements, you can usually tell what the most abundant isotope is in nature by simply looking at the average atomic mass. When you write the isotope symbol out, though, just remember that the mass number, these are the mass numbers, is always shown in the top left corner of the isotope symbol. So that's the mass number right there. Now, even though these mass numbers are listed for us, each of these isotopes has an actual atomic mass. So before we begin talking about that, let's remind ourselves of the masses of individual protons, neutrons, and electrons. So these are the subatomic particles that make up the atoms. And remember, we can round the proton and neutron atomic mass to 1 AMU, just round it. But in reality, it's just a little bit more than 1 AMU. So you can see that the neutron is slightly heavier than the proton, but just for our purposes, that slight difference is negligible. So for our purposes, we can go ahead and just say that each of these subatomic particles, the proton and neutron, are both equivalent. So they both are around 1 atomic mass unit, but they're actually not. Okay, there's more to it than just the whole number. So I just wanted to make you aware of that. And the electron, remember, that's a very small mass. The first real value, the first real integer, appears in the 10,000th place, and that's a very small number, even in atomic mass units. So we say that the mass of the electron is negligible. So it's not included in the mass calculation for an atom. Okay, so back to chromium. Now, remember I told you each chromium isotope has an actual relative atomic mass. So there it is. These are the masses of each of these isotopes. And notice if you round these relative atomic masses to whole numbers, then you will get the mass numbers here. So, for example, 51.940, that will round to 52. 52.94 will round to 53. 53.938878 will round to 54. Okay, so these are the actual relative atomic masses. And these numbers are what we're going to be using in calculation when they're provided. In addition to using the relative atomic mass, remember the pie chart? Remember how you can tell what isotope is the most abundant in nature? Well, these areas on the pie chart actually have numerical values associated with them. So if we're looking at chromium 50, which is this green section right here on the pie chart, you can see it takes up a very small amount of the pie chart, meaning it is rarely found in nature, is not as abundant as, say, chromium 52. So if we're looking at the fractional abundance, you can see how low this number is compared to the other values presented in this column. Now, typically you will see the abundance of a particular isotope expressed as a percentage. And the way you can convert this to percent is simply multiplying these numbers by 100. Now, if you know how to move the decimal over 2 places to the right, when you multiply by 100, you'll know that 0.04345 is actually 4.345%. Okay, now let's look at chromium 52. If we multiply its fractional abundance by 100, we get 83.789. So its presence in nature in percentage form is 83.789%. That's its that's its percent abundance. And then if we look at chromium 53, 53 is this light blue section here. So 53, if you multiply its fractional abundance by 100, you get 9.501%. And then finally, chromium 54 is this small red section there. So you can clearly see on the pie chart that it takes up the least amount of space on the pie chart, meaning it has the lowest relative abundance compared to the other isotopes. So multiply this one by 100 and you get 2.365%. So typically on our assignments, you will not see pie charts. You will see the data, the abundance presented to you in percent form. Okay. The fractional abundance, though, is useful when it comes to calculations, because in order to perform the average atomic mass calculation, you need the fractional abundance. So just as we multiplied by 100 to get the percents, to get back to the fractional abundance, all you would do is divide by 100. So now that we've looked at chromium, let's now take a look at another example of how to calculate average atomic mass and also understand the differences between mass number and average atomic mass. So we're going to start by looking at isotopes of oxygen. So here we have oxygen 16, oxygen 17, and oxygen 18. So think to yourself, what do these numbers represent? These are the isotope names. What do those numbers represent in the isotope name? Hopefully you recognize them as the mass numbers of each isotope. Well, in reality, these isotopes each have a specific relative or a specific atomic mass. And there it is. Okay, so the units here for all of these are AMU, or you could just say U. Okay, so remember these two units are used interchangeably. They mean the same thing. Okay, so this number here, because we're provided with a specific atomic mass, is what we're going to be using in our calculation to determine the average atomic mass for oxygen. Okay, so this is the atomic mass for each of the isotopes. Now, we're going to use that, I said, to calculate the average atomic mass, which is this number right here on the periodic table. Okay, so if you don't know anything about weighted averages yet, if you've never heard of that, you might be thinking, oh, all I have to do is add these three numbers and divide by 3 and I'll get the average. Well, no, that's not the case, because what we're going to be calculating are actually weighted averages, okay? So weighted averages are a little bit different. We'll get into how to calculate those in a moment. So to calculate the weighted average of all the isotopes of the element found in nature, remember, to get this number here, the 15.999, you need two pieces of data. You need the individual isotope mass, which is shown here, and you need the abundance, but not just the percent abundance, you need the fractional isotope abundance. Okay, so that will mean converting each of these percent values to decimal. So to do that, remember, divide all the percentages by 100, or you can move the decimal point over 2 places. Okay, and that'll give you 0.99759. Okay, because we need to get rid of these percents. Okay, so to get rid of the percent, divide by 100, and you would get 0.00037. And then divide this one by 100. Okay, divide this by 100 to get rid of the percent, and you would get 0.00204. Okay, so that's how you convert the percent abundance to fractional abundance. Next, let's go ahead and plug in the values. Before we do that, if you're somebody that needs an equation to solve a problem like this, there's one provided here for you. So just really quick, the percent abundance isotope, you would take that, divide it by 100, and that's how you would get the value that I'll show you in the calculation. So you need to divide all of these by 100, as I showed you on the previous slide, okay, to get that fractional abundance. Then once you have that, you're going to multiply it by the mass of each of the isotopes. So these are the isotope masses right here. Okay, so you'll do that for every set of numbers. So you'll multiply, 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 as shown here. You can see the The dot, dot, dot here at the end of the equation shows that you can do this for an unlimited number of isotopes. So in this particular equation, only two are shown, two setups are shown, but for oxygen, we actually have three isotopes. So we will have three multiplication products that we get. So the fractional abundance, remember, is calculated by dividing the percent abundance by 100. So that results in us getting these numbers here, these values down here. And then you would just multiply the isotope mass. So the masses are listed here. Okay. So now that we've set everything up, we'll do each section together. So for the first set of numbers, 15.995, this value has 5 significant digits present. 0.99759, this also has 5 significant digits. So when we calculate our answer on the calculator, okay, you're going to round your answer that you record to 5 significant digits. So our answer after multiplying is 15.956. Let's look at the next set of numbers. So 16.995 has also 5 significant digits. So I'm dealing with significant digits here. That's what I'm talking about. And the next set of numbers here, or 0.00037 rather, has 2 significant digits only. These are, remember, leading zeros, so they are never counted as significant. All right, so now that we have 5 and 2 significant digits, we want our final answer to have the lowest number of significant digits. So after multiplying, you should get 0.0063 as your calculated and recorded answer. Okay, finally, the last set of numbers, 17.999, that's 5 digits, significant. And then this value here, 0.00204, has 3 significant digits. So our final answer after calculating and recording, we should have 3 digits recorded. Okay, then we're going to line them all up. Okay, so the decimal places line up and add them, because you can see here, after multiplying the percent or the fractional abundance by the mass of the isotope, of each isotope, we're going to add, see the addition sign? We're going to add all the products together. Okay, so now here we go. This is the sum down here, 15.9990. Now remember the rules for significant digits when you're adding and subtracting. You want to go with the least precise value as the basis for recording your answer. So our least precise value is the first one, 15.956. It ends at the thousandths place. So that means our final answer must also stop at the thousandths place. So we will eliminate those digits there at the end and round our answer to 15.999 units or atomic mass units. And then remember, the whole purpose of this was to calculate average atomic mass. So this is showing you just how average atomic mass is calculated. Let's look at one more example of how to calculate average atomic mass. We'll look at the isotope chlorine 35 and chlorine 37. And chlorine 35 has a atomic mass of 34.969 units, so very specific there. And it has a natural abundance of 75.770%. So remember, we need to change that to a fractional abundance by dividing by 100. And then the next isotope, chlorine 37, has an atomic mass of 36.966 units and a natural abundance of 24.230%. Okay, so we're going to use the same equation, if that's helpful to you, and just simply plug in our numbers. We're solving for, remember, average atomic mass. So we're going to set that to equal the first fractional abundance, 0.75770, multiply that by the atomic mass of chlorine 35, which is right here. And then we are going to use the second natural abundance, convert that to a decimal, and then multiply that by its atomic mass. Okay, so again, if you're in honors chemistry, you've already covered significant digits. So in the first value, we have 5 significant digits. In the second value, we also have 5. So when we multiply these two, we should get 5 digits in our answer. And the same thing is true for the second set of numbers. We have 5 in this first value, 5 in the second value. So our answers for these products will be recorded to 5 significant digits for both. So here are the products, 26.496 plus 8.9569. So the reason why these digits are underlined is because of significant figures. So the thousandths place is where the first value stops, and that is our least precise value. So when we add these numbers together, our final answer should be recorded to the thousandths place, because this value is the least precise value, and that's what limits our answer. So we're going to round 35.4529 to 35.453 units. So that's our final answer for the average atomic mass calculation. Now, if you are in a general chemistry class, you can stop this video here. If you're in an honors chemistry class, you should continue watching. For this portion of our lesson, we're going to focus on how to calculate the isotope abundance. So we're going to look at indium, an element on the periodic table, atomic number 49. It has two naturally occurring isotopes, indium-113 with an atomic mass of 112.904 and indium-115 with an atomic mass of 114.904. The average atomic mass of indium is 114.818, and that's straight off the periodic table. Determine the percent abundance of each isotope. So before we begin to solve this problem algebraically, let's take a look and see if you can predict which isotope will be present at a higher percentage in nature. So the average calculation comes out to 114.818. And you're given two isotopes, indium-113 and indium-115. So you should be thinking about what the rounded value of the atomic mass comes out to. So you can see if you round 114.8 to a whole number, it comes out to 115. So the majority, or the higher percentage value, should be assigned to indium-115. That's one way you can kind of check yourself to see if your numbers make sense. And if you look at this pie chart, you can see clearly that 115, in fact, does take up the majority of the space on the pie chart. So it will be present with the greatest abundance. So now let's look at the steps on how to solve this problem algebraically. The first thing you want to do is to choose one isotope. Doesn't matter which one, 113, 115, up to you. And you're going to assign its relative abundance. Okay, you're going to assign that value the label X. Okay, then what you're going to do is take the second isotope and assign its relative abundance to be 1 minus X. Okay, now that you've decided what's what, okay, so for my example, when I was working this problem out, I assigned 113, indium-113, to have a relative abundance of X, and I made indium-115 1 minus X, its relative abundance. So you might be asking yourself, well, why is it 1 minus X? Well, if you look at the pie chart, the pie represents one whole. So the total is represented by 100%. Now, when you're calculating the percent abundance of indium-113 and indium-115, adding those values together should get you the total of 100%. If you take the 100% and divide it by 100 to get rid of the percent sign, you get 1. So the 1 representing the whole is where that one comes from. If X is indium-113, then 1 minus X will be the relative abundance of indium-115. So recall that the sum of the relative abundance will equal to 100% of the total indium found in nature. Okay, so if you are a formula person, you like formulas, then you can use this to guide you. So what you're going to do is take the mass of each isotope represented by the red M. So the M1 would be the mass of the first isotope that you assigned X. M2 would be the mass of the second isotope that you assigned 1 minus X. And then finally, the M that I've written here in blue, that's representative of the average atomic mass, because that is a value we are given or can obtain from the periodic table if we know what the element is. So now let's plug in some numbers. Remember, indium-113 is our X, indium-115 is our 1 minus X. So if we take the atomic mass of indium-113, it goes right here next to the X. And then indium-115's mass of 114.904 goes here next to the 1 minus X. You're going to go ahead now and solve algebraically by distributing the 114.904 to the 1 minus X inside the parentheses. So now that we've distributed, you're going to combine like terms. Okay, so we're going to subtract 119.904x minus 114.904x to get negative 2.000. So if you're following along with the significant digits, each of these values goes to the thousandths place. So the rules of subtraction mean that your final answer can also go to the thousandths place. And then now we're going to subtract 114.904 from both sides of the equation. Okay, giving us negative 0.086. Now to solve for x, we would divide both sides by negative 2, and that gives us the fractional abundance of indium-113 as 0.043. Because the question is asking for a percent abundance, you must multiply this by 100 to get the percent value. Now that we've solved for indium-113, which is x, we've solved for x, now we're going to solve for 1 minus x. So all we need to do is plug in the 0.043 into the x value there and subtract from 1. And when we do that, we get 0.957. Okay, once again, this is the fractional abundance. And because the value is asked, or the question is asking for a percent abundance, we're going to multiply this value by 100. So when we do that, we get 95.7% indium-115. Now to check your work, one thing you can do is add up your percentages. And if you are at exactly 100%, you know you're right. For our last example, we're going to take a look at a fictional element. So the average atomic mass of our fictional element covidium is 19.021 AMU, atomic mass units. It has two naturally occurring isotopes, covidium-19 and covidium-20. We're going to determine the percent abundance of each isotope and record each value to the 10th place. So the setup for this will be exactly like the previous problem, where we take one isotope and assign it the relative abundance of x, and take the second isotope and assign it the relative abundance of 1 minus x. Then we're going to plug in our masses. So this time, notice we are not given the relative atomic mass for each isotope. Instead, we're simply provided with the mass numbers. So if you are not provided the atomic mass, you are free to use the mass number of the isotope in your calculation. Okay, so now that we've plugged in our 19 and our 20, and also the average atomic mass given to us here, we're ready to solve for x. So go ahead and distribute the 20. Now we're going to combine like terms, 19x minus 20x, and that'll give us negative x. Subtract 20 from both sides. And then we solve for x, and we get 0.979. So this is the fractional abundance. We're looking for the percent abundance. So remember to multiply this value by 100 to get the percent abundance. When we do that, we get 97.9% of covidium as covidium-19. And then if you look at the next one, now we're going to solve for covidium-20 using 1 minus x. We're plugging in x here, 0.979, so 1 minus 0.979 is 0.021. This is, again, the fractional abundance. We're going to multiply this by 100, and that's going to give us 2.1%. Remember to check your work by adding your percentages up. If you get a sum of 100%, then you know you were on the right track. One other thing I wanted to point out is you could have predicted which percentage would be greater based on rounding the average atomic mass given to us to a whole number. So 19.021 rounds to 19. So covidium-19 rather, should be present at a greater percentage. And that's it for average atomic mass calculations and percent abundance calculations.